they're going to ask me, possibly, that they want me to prove de Moivre's theorem for n an element of natural numbers only. So it could be in your book for more than that, but you only need to do it for natural numbers. So de Moivre's theorem states this, and it's in your log tables. I might just get it because I want to make sure I'm using the correct language. Oh, there it is. Okay, so they use n, and they said that's equal to or to the power of n cos n times theta plus I sine n times theta. This is what de Moivre's theorem states. They want you to prove by induction that this statement is true, that when you work with the left-hand side, that it does equal to the right-hand side. Perhaps you might pause the video now, go through your 4 steps of induction and see how far you can get. Or maybe you want a quick reminder, well then watch and I'll just do step 1. Maybe then pause the video and try and do at least step 2 on your own. And maybe even to start step 3. Some of you will definitely be able to, you'll be able to get a good chunk of the way, I'd say, at least. Okay, so step 1. We're going to prove, so this is where we knock the first domino. We're going to prove that the statement is true for the smallest number possible, which in this situation is the number 1. So prove true for n equal to 1. So take the left-hand side and anywhere you see an n, throw in a 1. Take the right-hand side, anywhere you see an n, throw in a 1 and see, do you get, is that statement true then? So that to the power of 1 is apparently the same as, let's just check this. Now, is that true? So anything to the power of 1 remains the same. So that's or to the power of 1, that's or, and then 1 times theta. Yep, that's true. Step 2. We assume the proposition is true for n equal to k. And at some stage we will use our step 2. So we're assuming now is true for n equal to k. So anywhere I add an n, I'm throwing in a k. This is my assumption. Not probably, at some stage in step 3, I always use my assumption. Step 3, what am I trying to prove? I'm trying to prove the proposition is true for n equal to k plus 1. And what would that look like? It would look like anywhere I had a k, I'm now going to put in a k plus 1. hopefully all that is clear. And now this is what I'm trying to prove. So I'm going to take the left-hand side. I'm going to work with it and hope that I eventually get to the right-hand side over here. Okay? So I'm taking the left-hand side. Here's my proof. I take or cos theta plus I sine theta all to the power of k plus 1. And I mess around with this until I get to here. Okay, rules of indices. If I have two things multiplied to a power, I can split those out. Okay, nice. Look, I'm already there. That's nice. Again, my rules of indices say that if I have addition of powers, that can be written as multiplication. So my or to the power k plus 1 is perfect now. It's just this that I need to work on. So because I have plus here, that could have been cos theta plus I sine theta to the power k by cos theta plus I sine theta to the power of 1. Okay. Now, I guess now is where I become a little bit, I'm not going to say stuck, but now is the time where I think I would be trying to use my step 2. So this says that if you see this, you can replace it with this. Right, so I'm actually going to rewrite this as or to the power k by an or, that's again an indices rule, by the cos of theta plus I sine theta to the power k by the cos of theta plus I sine theta to the power of 1. I can just leave it like that. And can you see it now? This bit here, or cos theta I sine theta to the power of k, I can now replace with this. So I now have or to the power k sorry. I've actually highlighted that wrong. It's this bit. So if you notice, and this is actually very, particular, that it's all to the power k. So or by cos theta I sine theta to the power k, that or has to be the power k as well. So it's actually, sorry now, that and that I'm replacing with this. Now, just in case, I want to be sure you're happy with that. So my step 2 has this. So if you split each of those out, that's or to the power k by cos theta plus I sine theta to the power k. So it's that bit there and that bit there that are getting replaced by this, which means I'm left with or to the power 1 times what I have up here, times the cos of theta plus I sine theta. Okay, so now this little bit here can just go back into r to the power k plus 1. Just this little bit here. Times cos k theta plus I sine k theta by cos theta plus I sine theta. I'm going to multiply this out. Don't know what else to do. So that gives me cos theta by cos k theta. Cos theta plus cos k theta. And then cos. So I cos k theta by sine theta. So that's that by that. Now we have I sine k theta by cos theta plus I by I is an I squared. I squared is minus 1 times sine k theta by sine theta. Okay. So now this looks perfect. This is what I'm looking for. So I'm just going to show you here now what I'm trying to prove. This bit looks good already. It's really just how do I go from here to here? Let's have a look. We have ones that are imaginary because they have eyes, and we have ones that are not imaginary. So I'm going to look at the not imaginary first. So we have cos theta times cos something else, k theta, minus sine k theta by sine theta. Only place I'm going to get to rearrange cos and sine is back in my trigonometry pages. So, is there anything on my trig pages that are going to help here? And we have, so we're looking for, yeah, if you can see it here. So we have cos something by cos something else minus sine something by sine something else. Okay, so let's call, so we have cos, let's call that A, and cos B minus sine A, so that's A, because it has to be the same as to what I called A a second ago, by sine B. I could have just written that in the other order. Maybe I will. Okay, so I'm going to just rewrite the line, and these two just switched around. So we have cos theta by cos k theta plus I cos k theta sine theta plus I sine k theta cos theta minus, sorry, I mean to close the bracket, minus sine theta sine k theta. Now I can close my bracket. I hope that's okay. So we're calling cos A, cos B, sine A, sine B. What can that be replaced by? Cos of A plus B. So we have or to the power k plus 1. And then cos A cos B minus sine A sine B. You just replace with cos of the two added. theta plus k theta. So that's that bit cleaned up. If we take the I out in common, we have cos of something, sine of something, sine of something, cos of something. So let's do that again. Yeah, there it is. And again, I might just write that in a different order. So let's go for sine theta cos k theta plus cos theta sine k theta. Remember, stop the video at any stage that you need to. There's a lot of information here. This isn't difficult, it's just there's an awful lot of cos theta, cos k theta, all that sort of stuff. So now, if I look at this bit here, because I'm taking the I out in common, then I will have sine A, cos B, cos A, sine B. So sine A, cos B, cos A, sine B, that can be replaced by the sine of the two added. Okay, am I nearly there? Yep. I'm going to take the theta out in common. My r plus 1 is perfect. Or my r is the power of k plus 1. Then I have cos of, take your theta out in common. And we're done. I'm where I want it to be, up here. I took the left. I got it to mess around with it. I needed to use my log tables a few times. Needed to be able to multiply out, etc., etc. And I now need to just finish off with my step 4, and you know, by induction, de Moivre's theorem is true for all n an element of natural numbers. You know, you can just finish off with your typical step 4.